Hello, welcome back to Math 152. Today we are going to look at two more examples from section 7.4, which is integrations using partial fractions. So let's look at the first example. So you are asked to evaluate the following definite integral, and you see that this thing here is actually a rational functions. So a rational functions is a functions that consists of the divisions of two polynomial. So you have p of x and q of x. So the polynomial is expressions that looks like this, where the n here is actually a natural numbers. So not only that, we also call that this n here as the degree of this polynomial. So if you look at this particular rational functions, so the numerator here is actually consists of polynomial of degree 2, and the denominator here is actually a polynomial of degree 3. It doesn't look like this because it's already been factored. So sometimes it doesn't factor it for you, and you have to like try to factor it out. Or sometimes they want to make your life easier, they will actually put it in a factor form. So remember that since this is a polynomial of degree strictly less than this, so we know that we can split them up like that. And also remember that we only use this information here one time. We only look at this polynomial here one time by looking at the degree. Once we determine that this degree is strictly less than the polynomial, the degree of the polynomial for this expression here, the degree of the polynomial in the denominator, then we are no longer going to look at this like ever again. So for example, when we decided to put this a, b, and c, that is not determined by the expression 4y squared minus 7y minus 12. So we only look at it one time, and actually we don't actually care about what are the details about all these coefficients. We only look at the degree. So this is degree 2, this is degree 3, so we can split them up like that. And since you can write all these things as a linear factors, so we know that these are just constants. And also, because this is linear factor, they're all linear factor, so we can use a shortcut, which is the cover-up rule, which is, so for example, you want to find a, so you will cover up this term y and substitute y equal to 0, which is the thing you cannot substitute, so it's just being naughty or something like that. So substitute everything here with 0, so as your computation here shown, that you will get 2, and that 2 will be the value of this a. So a will be 2. That's what cover-up rules means. So for example, if you want to find b, and you want to take this shortcut, you can cover up y plus 2. Okay, so you know that y cannot be equal to negative 2, and this is the one that you purposely substitute into this expression. So if you do that, you will see that the answer for b is 9/5. So this is again what we call the shortcut, which is the cover-up rule. So for example, if you want to find c, you will cover up y minus 3 and purposely put y equal to 3 to the entire expression here to get the value of c. So if you do that, you get c is equal to 1/5. Now, so this is a non-traditional method. It's just a shortcut. So the proper way of doing it, you can also try to do the proper way, which always works though, not only for linear terms here, but it also works for all partial fractions, question related to partial fractions. That method is to start from here, okay, and then cross multiply this entire expressions here, here, and here to get this. All right, now you have two choices here. One is to multiply all this thing out, and regroup all the terms so that you can find all the coefficients for y squared right here, find all the coefficients for y here up here, and this is the constant. Now you, by comparing the corresponding coefficients, so we know that a plus b plus c has to be 4, and then these terms here has to be -7, and then these terms here have to be -12. So because of that, you can get this a, b, and c easily, and you can also compare it to what we have found just now. They are exactly the same. So that is how you usually do it. If you don't want to use any special rule, this is the method that will always work. I also have a quick comment here. So sometimes, especially when situation is very complicated, you might not want to multiply everything out. We can still compare coefficients just by looking at this. If you look at this line alone, you will see that in order to get y squared, so y squared will have to come from here. Okay, so let me say that again. So in order to get y squared will come from here. This will not give you y squared. This will only give you terms in y. This also only gives you terms in y. This actually gives you only a number. So in order to get y squared, so you will see that you get y squared from here. So the coefficient for y squared, you know that one of them is going to be a. So here, this is the one that get you y squared. So you know that that's a b. Okay, and here, that is the one that get you y squared. So you know that that is the coefficient for y squared coming from here. That's a c. So you can also see that a plus b plus c has to be equal to 4. So so we don't have to multiply everything out. We can just, by looking at this, you should also be able to identify which are the coefficients. Now, for example, how about the coefficient for y? So as I said, this is giving you y squared, so that's not what we want. So this is the one that gives you y. This is also the one that gives you y, right? So altogether, the ones that give you y here will be how many of them? So you will have minus 3 plus 2, so you have minus a. That's how many of it you have for y coming from here. This one give you y squared. This one give you y. So you have minus 3b for the y, okay? And here, this give you y squared. This give you y. So you have plus 2c here. These are all going to give you these are all coefficient for y, which is exactly this, minus a minus 3b plus 2c. So it has to equal to negative 7. So sometimes you can also just try to find the coefficients without multiplying things out. This is pretty easy. You can multiply all this thing out, but when your partial fraction is very complicated, you might not want to multiply out. It takes too long or something. You can actually just see it and do it in your head to identify which combinations of the y will give you y squared, which combination will give you y, so on and so forth. So once you have all these coefficients, the rest is easy now. These are the coefficients that we got. And here, if you see you're integrating all this thing, you will know that this immediately turn into the log. And then the one last thing to do is to, since this is a definite integral, so you're going to put all these limits in. And be careful though, just make sure that you remember that when you integrate fx and then f prime of x dx, what you get is not log of fx. Okay, it's not log of fx, but the absolute value of log of fx. So which means, for example, if you look at this term here, when you substitute, you get log of negative 1. So it will not, log of negative 1 is not something that is defined. You know, log only takes strictly number that is strictly positive, but with this, it means that you have log 1. Okay, so you have to be careful, otherwise you'll run into trouble when you substitute. So you can do all these computations, and you'll see that your answers is going to be this. So this is a pretty straightforward example. The second example is also pretty straightforward. So again, this is a rational function. This is a polynomial with just a constant term, and this is a polynomial of degree 3. So obviously we can split them apart, but because so this is a constant term, so this should be 1 degree less than it. So you have another constant term. This is not a constant term. This is a degree 1 polynomial. So this has to be a degree less than it. So it's going to be a constant terms. So this is a polynomial of degree 2. So this is 1 degree less than it. So it's going to be a polynomial of the form bx plus c. And we are going to find the constants a, b, and c. And the way we do it is to cross multiply this thing here and here to obtain this equation. All right. So as you can see, if you look at the coefficient for x squared, you will have a, you will have b, right? So you have a plus b equals to the coefficient for x squared here, which is 0. You should see 10 as 0x squared plus 0x plus 10. So you have a plus b equal to 0. See, I'm not multiplying all this thing out, even though I can. So how about coefficient for x? So there's no coefficient for x here, and the coefficient for x is not come from this one, but it's coming from here and also here. So you will see that b plus c that's the coefficient for x, and will also have to be 0. Sorry, this is minus b, so you also have to be 0. That's the reason why you get this equation. And finally, the constant terms were coming from here, and the constant terms will be coming from here. So that's the reason why you have 9a minus c which has to be equal to 10. So once you have these three equations with three unknowns, you should be able to find this unique solution. A is equal to 1, B is equal to -1, and C is equal to -1. So just make sure that you know how to partial fraction it properly, and make sure you do your algebra correctly at this stage. Then the questions is not going to be very difficult. So once you split this thing to this, you can further decompose it by writing it like this. Actually, you still doesn't really know why we have that terms yet. So by splitting them apart, you get this expression, and then we will know the integral of this is going to be this. Now the integral of this is going to be something that to do with arctangent. We might need a little bit work on that, and then here we can easily see that this is the fx, and the f prime of x is 2x. So this is a substitution. U equals to x squared plus 9. So du equals to 2x dx. So I need a 2x dx to make a du. That's the reason why I make up a 2, and then I divide the 1 over 2. So the 2x dx is going to give me du, and then this is going to give me u squared plus 9. All right, so you are basically, so this is going to give me just u, sorry. So you're going to have 1 over 2 du over u. So you know it's log of u, absolute value of u, but then x squared plus 9 is always strictly positive. So you can drop the absolute value sign if you want to. All right, so this part here is a little bit more involved. So if you remember, the basic formulas for arctangent is that the integral for x squared plus 1 dx, this is going to be arctangent of x plus c. But this is not 1. You have a 9 here. So one thing you can do is factor out the 9. And then this will be x squared over 9, which can be written as x over 3 brackets square. So now you use the u substitution so that it will change into something that looks like this. So obviously this, you want it to be u. So you have to need 1/3 dx in order to make du. I have 1 9 here, so I can split them into these two parts, because this is actually 1 over 3 times 1 over 3, which is 1 over 9. So I gave 1 over 3, move 1 over 3 here, so that I have 1 over 3 dx. That makes du. This makes u squared plus 1. So now we can back to this form and get arctangent u times 1 over 3 plus c. So your u is x over 3. That's the reason why you have that. So as you can see, it's not very difficult at all. The main decomposition happened here. Okay, main decomposition happened here. This is the algebra part to make sure that you get the coefficient correctly. And then once you have the coefficients, the rest is typical integral involving the things that, you know, you have to know. Things that you learned from the previous sections and all that. Everything is cumulative, so you better make sure that you know everything that we learned before. So as you can see, partial fractions problem is usually pretty easy to identify. One comment though, you have to be very careful about the question. So if you see x squared plus 9, this is how you do it. If you see x squared minus 9, you will have to split it into x minus 3, s plus 3. So you will have to partial fraction something that looks like this to a over x minus 3 plus b over x plus 3. And the question that you get, the answer that you get, is going to be very different from this. You will not have arctangent. You will have log of something plus x minus 3 plus log of something. So it's going to be very different from here. So you have to be careful whether or not this is a plus or this is a minus. It will make a lot of difference. And this is like two more example for the section 7.4, which is integrations involving partial fraction. And that's it. I'm going to see you tomorrow, and have a good night.